In this last section, we're going to look at another application of statistics, and this is on scatter plots, correlation, and regression lines. And I will say I did copy a lot of the pictures and text from your actual text, so please refer to your text, to see it a little bit better and blown up. It was just a lot of key definitions and stuff there. So instead of going back and forth between the text and the paper, I just figured I'd put it all on the paper to make it easier for the lecture. But again, this is all from your text from this section. So first of all, a scatter plot, an example of a scatter plot is what you have on the left. So a scatter plot is when you have two variables, so typically an X and a Y variable, and you're plotting the data, and you just plot it as individual points. You're not going to actually connect the lines together or do anything like that yet. So your scatter plot is really just plotting all those points. So what we're looking at here is we're really trying to answer a question of, is there a relationship between two different variables? So in the example we're going to look at, this has to do with your level of education and also your prejudice level. So our question here that we're looking at is there a relationship between, and again, in general, it's whatever two variables you're studying. Here we're looking at education and prejudice. So with increased education, does a person's level of prejudice tend to decrease? Notice that we're interested in two quantities, so again, two variables. In this case, it's years of education and level of prejudice. And then for each person in the sample, they recorded the number of years of school completed and the score on a test measuring prejudice. Higher scores on this 1 to 10 test indicated greater prejudice. They used X to represent the years of education and Y to represent scores on this test. And this table here shows the data for 10 random people, so a sample of 10 people. So for instance, person A has 12 years of education and they scored a 1. Person B has 5 years of education and they scored a 7. Person C has 14 years of education and they scored a 2, and so on. So each of these columns represents an individual person. When two data items are collected for every person or object in the sample, the data items can be visually displayed using a scatter plot. So again, we have a visual diagram or a picture here. A scatter plot is just a collection of data points, one data point per person or object. And we can make a scatter plot of the data in this table by drawing a horizontal axis that represents years here and a vertical axis that represents their score on the test. They represented each of the 10 respondents with a single point on the graph. So for example, the dot for respondent A is located to represent 12 years of education and 1 on a prejudice test. So here's A right here. You can see that it lines up with the 12 for years of education, and then it lines up with the 1 on the prejudice test, which matches the data that was in the table. So it's just a regular graph, but with meaning. And we did this for all 10 values here. So a scatter plot like this can be used to determine whether two quantities are related. So if there seems to be a pattern. If there is a clean relationship, the quantities are said to be correlated. And what you're going to see here is you're going to see some sort of pattern in the graph. Now, for our purposes, we're going to focus on linear patterns or lines, but there are all other different kinds of correlation too. You could have a pattern that's more of a U-shaped, or maybe it's a wave shape. It could be what's called an exponential, so it kind of starts slow and then shoots up, etc. So there's lots of different patterns that we look for in different kinds of correlation. We're going to focus specifically on linear relationships in this section. So if we look here, we do kind of see a downward trend in the points. So as we read this scatter plot from left to right, I do see a downward trend, which is kind of implying that as the years of education increase, that score on the prejudice test is decreasing, right? It's going down. So correlation is used to determine if there is an actual relationship between two variables, and if so, the strength and direction of that relationship. So by direction, they mean, is it negative, so it's going down, or is it a positive direction, meaning it's going up, just like slope. Negative slopes go down, positive slopes go up. Okay, so correlation is there a relationship? But we check it mathematically. So the first thing we do when we have real world data is we typically make a table and we graph it. So visually, we look at it first and we say, okay, does there look like there's a pattern here? So if I look at this, it looks like there's a pretty clear pattern to me of sort of a decreasing trend here. It looks pretty linear. Real world data is never going to be perfect. So you're never going to see points perfectly line up. It's just not going to happen. So this looks overall pretty linear though. So visually, I'm thinking, yes, there does look like there is a relationship here, right? It looks like kind of a linear pattern. But what we do is we actually do some math calculations to prove that. So let me move my thing up a little bit here. Correlation and causal connections. Correlation can often be seen when data items are displayed, again, like I said, on a scatter plot. That tends to be our first step when we have real world data, is to graph it and see what it looks like first. Although a scatter plot may indicate correlation, we cannot conclude that one variable causes the other. And this is a really big idea. Correlation does not necessarily mean causation. So because two things are related or have a relationship does not always mean that one causes the other. Okay, so that's really important. When we're actually talking here about showing if two things are correlated, we're just showing that they have a relationship together. We're not saying that one is causing the other to occur. Those are actually two different ideas. So if we're talking about education and prejudice, there could be at least three possible explanations for why we see a pattern, right? We see that kind of decreasing pattern. The first explanation is that there actually is no causation and the correlation is simply coincidence. So maybe the correlation between increased education and decreased prejudice is simply a coincidence. We just happen to get 10 people and it was a pretty small sample and maybe it looks like there's a relationship, but actually it's just a coincidence. If we had had a larger sample size, maybe we wouldn't have seen that. So the second thing that could happen is that maybe there's an underlying variable, which is the real cause linking these two things, right? So for instance, education usually involves classrooms with a variety of different kinds of people. So perhaps it's not so much the increased education, perhaps it's the increased exposure to diversity in the classroom setting, which happens to go along with education, but maybe that's the real reason why people with more education are showing less prejudice, right? Maybe it has nothing to do with the idea of education, but the fact that they are exposed to more diversity, more diverse people, more diverse ideas. So that actually is what's causing the relationship. Or maybe one thing really does cause the other, right? So maybe education, the process of acquiring knowledge, requires people to look at new ideas and see things in different ways. So perhaps, yes, education does actually cause people to be more tolerant and less prejudiced. Okay, so when we see a relationship on a graph, or we're talking about correlation, we are not saying that one is causing the other. We are saying that we are observing a relationship there, but that's as far as we're going. To actually prove that something causes something else is very, very difficult. It's not as simple as just doing a quick correlation calculation like we're going to do here. It's a lot more difficult. So we may be able to show that two variables are related, but to actually show that something is causing something else is beyond the scope of this, beyond the scope of basic statistics. So you're doing additional research to prove that that's the case. All right. Another interesting example too that I kind of always remind students to think of is, so this is an old one that I've heard years ago. It's kind of a sad one, but it's if you think about drownings and you think about ice cream sales. So as ice cream sales increase, drownings tend to also increase. And if you think of it, there's one is not causing the other in this case, right? Ice cream sales are not causing drownings. The fact is that they're both linked by temperature. So the increase in temperature is causing people to buy more ice cream. And it's probably also causing people to swim more, which would then end up with potentially more drownings if more people are swimming and maybe, not being as careful as they should be. So that's just an example where, even though these things have a relationship where they're both increasing together, one is definitely not causing the other. There's an underlying variable there. So we just want to be really careful about what we're saying when we look at these graphs. All right, so let's get a little bit more into the math here. So regression lines and correlation coefficients. So this figure here is the original data set we were looking at. It shows your scatter plot. And it also shows a straight line that seems to approximately fit the data points. This kind of line is called the regression line. So it's a line that best fits the data points in a scatter plot. Notice that most of the data points lie either near or on the line. So usually not all the points are going to be on the line, but they should be close to the line. And the regression line is the particular line in which the spread of the data points around it is as small as possible. So this line is kind of like the best model we have to mimic the data, see what's going on there. It's like our model for the data. A measure that's used to describe the strength and direction of a relationship between variables whose data points lie on or near a line is called a correlation coefficient, and it's labeled as R. So here you have lots of different examples of different scatter plots with their R's as well. So let's look through some of them. Variables are positively correlated if they tend to increase or decrease together. So you're going to see, some sort of trend like this where they're going to be increasing together or decreasing together, going backwards. They are negatively correlated if one variable tends to decrease while the other increases. So think about a negative slope. It looks more like this. Okay, so this is your positive correlation. This is your negative correlation. Now, that correlation coefficient R, which I'll show you how to calculate in a little bit, is always between -1 and 1 inclusive. So figure right here, 1230A, shows a value of exactly 1. So if you have a value of exactly 1, you have perfect positive correlation. So they are perfectly on a straight line. And in the real world, that's probably not going to happen. You can get close to 1, but you're probably not going to be on 1. So if you have R equals 1, it's a perfect line, fits it exactly. Usually what happens is something in between. So here's an example of a positive correlation. So you can see R is positive. It's 0.8, so it's close to 1. So it's a very strong positive correlation here. Now here R is about 3. So you can see that you're still kind of having this positive trend. It does kind of look like things are increasing, but it's really not as closely knit, not as much of a line, more of like a group, right? So, and that R is smaller, it's 0.3. So it's still positive. So I do see some positive correlation here, but because the value is closer to 0, it's much more moderate or weak. An R of 0 shows absolutely no correlation. So if your R is very close to 0, then you don't have very much correlation there. Now here you are the other way. So this way, again, if you read your graph from left to right, it does look like this group of data is kind of going downward in a line, but it's a little bit more spread out. So you're noticing an R of -0.3. So again, a lot closer to 0 here for that value. Here your data looks much more linear. Your R, you can see, is closer to -1. It's at -0.8, so you have a strong negative correlation. And when R is -1 exactly, you have perfect negative correlation. So those points really do lie on a straight line. And again, in the real world, you're probably looking at, if you have a very strong correlation, something like 0.9 or -0.9, you're probably not going to be exactly at 1 for real world data. Okay, and I'll let you guys kind of read through again some more details here. Let's look at one example. In a 1971 study involving 232 subjects, researchers found a relationship between the subjects' level of stress and how often they became ill. The correlation coefficient in the study was 0.32. So our R here is 0.2. Does this indicate a strong relationship between stress and illness? Well, let's think about what we just saw here, right? So 0.32 is pretty close to 0.3 or 0.30. So it really is not that strong. There's definitely a positive correlation there, right? If it's positive 0.3 or positive 0.32, these are going to look very similar, but it's not very strong. So I would say that there's probably more of a maybe moderate or moderate to weak positive relationship between stress and illness, at least based on this particular study, right? So things may be different now with current studies, but in 1971, using this correlation coefficient, we would say that, yeah, there's definitely a positive correlation there. So as you know, as stress increases, illness does increase. As stress decreases, illness decreases, but it's not super strong, right? It's more moderate or moderate to weak because that value is closer to 0, not closer to 1.